Hi, so this is problem 2.142. So you have here a free vibration since you do not have any input, and we're still talking about single degree of freedom system of damped because you do have a damper here. So we can see that you have this bar pivot at point O. Okay, so this thing will move kind of like a rotation at an angle of theta. So you can actually write the free body diagram. Okay, if you read the question, basically we want to come up with the EOM. So the overall problem is basically you want to find the free body diagram, the EOM, and then you want to find the natural frequency of the system. All right. So let me just recap of the overall for a free vibration, the general form on how you're gonna get the natural frequency is basically if you have system of linear system, you can actually write it x double dot plus 2 zeta omega n x dot plus. So this is the general form of how you can get some of the parameters if it's a singular freedom damped vibration. Okay, so if it's rotational, so you can also write as 2 zeta omega n theta dot plus omega n square theta, right? So from this general form, you can always find any parameters such as the zeta as also omega n given all other values. So you may want to rearrange your EOM in this form basically. So in this case, we want to rearrange the EOM in this form. And then you can figure out what will be your omega n. Right, so let us move on. Okay, how do we actually draw the free body diagram? In order to draw the free body diagram, you look at, you have to assume the direction. So first you assume the direction. So in this case, they already gave it to you, just by looking at the arrowhead there. So the counterclockwise is actually positive in this case. And the second thing, once you have the assumed direction, the second thing is you have to draw on the elements on the spring or the damper in the same direction of this assumed direction. So in this case, it has to be clockwise. Okay, the third thing is only you draw on the mass. So in this case, the mass or the J naught is basically on the bar. Then in this case, then only you draw action, all the action reactions. Okay, all the action reaction forces, okay, or moments on the bar. So that's the basic step. Okay, you always draw physical things on the spring of the damper and action reaction on the mass of the bar. So in this case, it's counterclockwise. So you would imagine that if the bar originally like this, so it will actually eventually it can actually go like that. Okay, so if you think about it, think of what happened to your k if you are being sorry, maybe I just get that again. Your red color is like that. So think of what happens at that point, and at that point, what happens to the spring and the damper. So if I want to draw it here, I put my, so I'm gonna see that my 3K would actually goes down, because that side would go down, and then you have your C. Okay, so this C would actually goes up. Okay, it's being compressed, and same as my K, because your okay will also goes up. Then let me just draw the action reaction. So all the C and K will go up, but 3K would actually goes down. So that's what happens as you pull it counterclockwise. And then only you draw the third part, is then only you draw the action reaction. Okay, so let me just color it. Let me just recap how you draw your free body diagram. So first part is your assumed direction. So your assumed direction is theta. You have that, which is counterclockwise. And then you have your draw on the spring. So you have these arrowheads going down, up, up. Okay, and then you have the final one, okay, which is the third step, is draw an action reaction. You can see this arrowhead going up, going down, and down. So it's opposite. So those are the 3 steps that you can do for your free body diagram. Okay, now you want to write your EOM. Okay, after you've done with your free body diagram. Okay, so then you can write, if you want to write your EOM, alright, so you are just concentrating on the mass. So you do not need to think of the rest. You just focus on the mass. Okay, so you always write on the based on the forces on the mass. So let me just put it up a little bit, because we already have our all the forces. So we are referring to the red part of the figure, which is just this one. So you are just focusing on this bar here. So the way we write it, you can see that there are 3 forces there, from the 3K, from the C, and from the K. There are only 3 forces. Okay, before sorry, we haven't finished actually the free body diagram. Before we go on, okay, the 3K, the forces, you have to write all the forces. So let me just maybe write that in a different color. So all the forces, the way we write it, you have to look at in the problem they give you the distance. Okay, so this distance here is 1 over L over 4, and there are distances. So these distances is like you are having a small triangle, if you can remember. So this moves at theta. Okay, maybe I blow it up a little bit. However, you would write the forces. Yeah, so in this case you have this small triangle, and it moves theta. So that means this 3K will have a displacement on its own, if I call it x. So the radius here is L over 4. So the way we write the displacement for the 3K, okay, is basically x is equals to L over 4 theta. Okay, so the way we write the forces will be 3k L over 4 theta. So that's how you write the forces there. Okay, then we go to the C. Okay, how do you write the forces for the C? Okay, maybe I want to draw again. Okay, there's also a small triangle here where it actually have theta. Okay, so basically C is also a linear damper. So the way we write it, assume your displacement here is x. So this x and the radius here is L over 4, as you can see here. So the same thing. Okay, the way we write it is, but this time it's supposed to be x dot. Okay, so then you would have your theta dot there. So x is equals to L over 4 theta. So the way we write the force is supposed to be C theta dot, because this is rotational. Supposed to be Cx dot, because this is linear damper. So but your x dot is basically L over 4 theta dot. So the way we write your Cx dot is basically L over 4 theta dot. So do the same thing for the k here. Okay, so this k it consists of this larger, maybe I just delete this so that it won't be confusing. So this k consists of a larger triangle, still theta. Okay, so the displacement here, if I call it x, so this x is equals to, so L over 4 plus L over. So if you add this up, you get 3/4 L. Okay, so the way we write the displacement for the k is 3 over 4 L theta times theta. So the way we write our forces now is basically your k times 3 over 4 L theta. Alright, so we have all the three forces explained, and we can also write on our free body diagram, so don't forget to write that out. Okay, so now your free body diagram here, it should be 3k L over 4 theta, and here it should be just now C L over 4 theta dot, and here it should be k 3/4 L theta. Okay, so we've done with our free body diagram. Sorry, just now I forgot to write the forces. So notice that all the forces are linear, from linear springs and linear. It's not a rotational damper and rotational spring. So that's why we have to convert from x to theta. Okay, then when you want to write, you have to write in terms of moment. So the way we write it has to be summation of moment, and you have to think of as we assume the direction of counterclockwise should be positive. Okay, so you look at the arrowhead and go from here, and then you see it's basically clockwise, so that's why you get a negative 3k L over 4 theta. And for C, okay, you look at the arrowhead here and this point here, so you go like that, so that's why it is also negative. Okay, negative C L over 4 theta dot. Okay, let me just erase that again, because actually I forgot, you have to times, so this is force, okay, you have to times the distance. So the distance is, again, this distance is basically L over 4 just now, okay, if you remember. So you have to times L over 4. So basically this is the force, okay, this is the D, the distance, because it is in terms of moment. Then you do the same for CL over 4 theta dot, okay, and then you have to times the distance is also L over 4. Same with the K, so you go from this point and you go to the arrowhead, so you can see that it's like that. Okay, so it is clockwise, so it's the same, it's negative K 3 over 4L theta times 3 over 4L. So everything has to be times with the distance. Okay, now we have to just rearrange. Okay, once we get that, you collect all the terms for theta together, and then you put everything to the other side. You also have the theta dot because you want to put everything to the other side of equation. So if you actually do that, you can see that you bring the theta dot, so that will be L square over 16. So because you only have theta dot once, only one term for that, so you can clearly write that out. And then if you do this, is basically you have 3/4 K, so L over 16 here as well. Okay, you collect the terms for theta. If you do that, then you get 3 over 4. Okay, you can check that out later. Is equals to 0. Okay, so now you do have this general equation, but you want to be able to write it in the in this form just now. Okay, you have to put everything in this form. So you have to divide all through with your theta, with your J naught basically. So if you want to do in terms of that, so you have J naught L square over 16 theta dot, and then this one as well, you have your 3/4, okay, everything divided by J naught. Alright, so 0 is 0, so everything divided by J naught. So basically this will be your, just in case in these questions they ask you to find zeta, and given all the values, so basically this will be your equivalent. Okay, this will be your 2 zeta omega n, and this one will be your omega n square. Okay, there are also some questions that they want you to get your J equivalent. So in this case, this is just your J equivalent. Sometimes they ask for your K rotational equivalent. So this will be your K equivalent, and this is like your sorry, I have extra points there. Okay, so this will be your C equivalent, and this will be your K equivalent. Alright, so then depending on the question, so in this case they ask you to find the omega n. Okay, so you can write your omega n. So your omega n is equals to square root of 3 over 4 KL square divided by J naught. Okay, so normally if you have a bar problem like this, the typical J naught for a bar, okay, you can see that this problem, okay, the bar is located, the pivot point is located outside of the, it's not at the center of the gravity, is at L over 4. Okay, so you may want to find, there's an equation how you would get J naught for this bar. Okay, so the formula is basically J naught is equal to J bar plus J at center of gravity. Okay, so normally in the test or in the final we will give you all the equations. It's just this one because your bar, your pivot point is at L over 4, whereas your center of gravity of the bar is normally at L over 2. So this is what we call the center of gravity. So any rigid body, homogeneous rigid body, normally the center of gravity is at the center. So formula for J bar is 1 over 12 ml square. So this is quite standard where you can actually look at in your textbook, okay? And this J for your center of gravity, sorry, I have cancelled that out. The J bar is basically the J standard from the table at its center of gravity, so which is 1 over 12 ml square. This you can find from the table. And then the md square is just the mass of the bar times d. So d is basically the distance between the center of gravity and so this is d, okay, the pivot point. Okay, so this is the pivot point. So d is the distance between the pivot point O, in this case, to center of gravity. So in other words, if you look at here, original problem, you can see that the center of gravity, maybe it's a bit clearer here, the center of gravity is actually here, same as where your C is. So the pivot point is here. So your D is basically L over 4. Alright, so we do the same thing here. So your D is L over 4 square. Okay, so you need to solve for your J naught to get your omega n, no? If we give you all these equations, but for J bar is quite standard. J bar is center of gravity. This equation, how do you get this equation? This is basically, if you remember last time, for your moment of inertia, at other than at center of gravity, you have to use this equation. Yeah, in statics, maybe you have learned this. So then you simplified. If you simplify, you should get 7 over 48 ml square. So then you substitute into your equation of omega n, then you should get your 3/4 of square root of your KL. So your K L square, then you divide it by 7 over 48 ml square. So you can actually cancel that out and you should get, okay, so finally this is your final answer. So you may want to simplify. If you have this kind of problem, you need to simplify the in terms of omega n, in terms of your calculated J naught. Okay, that's all. Thank you.